Okay, so thank you everyone for coming. This is our seminar number 111, and Professor Dali soon will give a second seminar in the series. I don't remember what was the number of the first. Do you remember?
64, I guess.
About 64. So about halfway in the series up to now. So Professor Sun is at North Carolina State University. He got his bachelor's in 2004 from Beihang University in Beijing, and then a PhD in 2009 at the Institute of Physics in Beijing. And then he moved to Oak Ridge National Lab as a postdoc, and then from there to University of Utah, also as a postdoc and then research assistant professor until 2016. And then in 2017, he moved to North Carolina as a faculty member, where he's now associate professor at the Department of Physics. His research interests are in spintronics and optoelectronics of organic semiconductors, magnetic thin films, and inorganic hybrid perovskites. And includes the studies of organic spin valves, light-emitting diodes, hybrid perovskite optoelectronic and spintronic devices, and the physics of those devices. So Dr. Sun is one of the pioneers who launched spintronic studies in hybrid perovskite materials. And his talk today will be about chirality-induced spin selectivity effect in two-dimensional chiral hybrid perovskites, particularly about chiral-phonon-activated spin Seebeck effect. So I look forward to your talk. Please take it over.
Thank you, Kirill. Thank you for the nice introductions, and it's my honor that I have able to have second chance to present it here. I really appreciate the committee giving me the opportunities. So yeah, well, my background in as Kirill introduced in the spintronics, in the hybrid perovskite and organic semiconductors. So now we also now we study studies for the chirality-induced spin selectivity effect with the CISS effect, getting a little bit of hot topic right now, typically in hybrid perovskite. So again, this work was supported by the DOE FRC choice and the DOE grant, also the NSF. Great. All right, so I will give an outline about my talk, about the introduction, about also connection between the CISS effect, the chirality-induced spin selectivity effect, and spin Seebeck, and also chiral-phonons. So then I will introduce our work about how to generate the transfer temperature gradient, how to convert the chiral-phonon into spin, and how to validate it using spin transfer torque, calculation, and comparison between the different effects and the conclusions, right? All right, so I think I don't have to spend much more time for the introduction about the spintronics. Everyone is expert in this field. So basically, we are able to convert the electric current between spin current, like using the multiple method. One way between these two currents you can achieve by the spin Hall effect and the inverse spin Hall effect. So we also, in spintronic field, we study the manganon, then you have a spin pumping convert from manganon to spin current, and also spin transfer torque, right, from the spin current to generate the manganons. And then you have phonons and other quasi-particles. By the connection between phonons and manganons, you have phonon drag manganon effect, you have spin Seebeck and spin Peltier effect, all kinds of conversions between different quasi-particles, right? So most of the time when you talk about the spin interaction between spin current, manganon, phonons, you need magnetic materials, right? So you need excited phonons in the magnetic material, excited manganons, the magnet convert to the spin current, then the spin current we're able to convert to electrical current using the inverse spin Hall effect, right? Make such a loop. So now they're coming out a new mechanism that directly convert between electric current and spin current without using any magnetic materials, just by harvesting the chirality. So that's the chirality-induced spin selectivity effect. So that's the effect was invented by Lolama and David Wodak back to the 2004. They have very nice review paper to talk about why, how the chirality can induce such a spin selectivity effect in any almost most of the chiral materials, right? So the chirality-induced spin selectivity effect means they call like a CISS effect, or some people call it KISS effect, right? So let's say CISS effect. So once I have an electron passing through a helical structure materials, and the spin, then due to the spin filtering effect in the beginning was understood like spin filtering effect, the spin polarization of the electron will be polarized. So you generate a pure spin current after you transmitted the helical structure. So this spin polarization direction depending the helicities, depending the handedness of a chiral structure. For example, you have left-handed, you got a spin down. If you're right-handed, you got a spin up. So this effect which have been persisted at room temperature. And if you calculate the Zeeman splitting by effective magnetic field, almost like a 90 Tesla to achieve such an effect. So once the effect was reported, including many research in the DNAs, in the chiral molecules, it's really introduced a new mechanism, introduce a spin current. So the first work was to demonstrate like real CISS work was demonstrated in the DNA system in the back to 2011 in published Science. They use the photon emission technique to study how once you have electron passing through the DNA structure and you detect the spin polarization of a photon electrons, and they realized the spin polarization was generated after passing through the DNA. And then later on, people, the Wodak, Lolama continues to discover more chiral materials that can exhibit the CISS effect. For example, in the chiral molecules, right, or their device configurations, the cysteine effect, in the cysteine and the left and right cysteines, and they make it into the traditional like a spintronic devices with only one magnet layer. So you pass the current through the chiral molecules, generates spin polarized current. The spin polarized current tunneling through the aluminum oxide into the nickel, and you got the magnetoresistance. And then if you switch the magnetic field of the ferromagnet of the nickel, you got the magnetic hysteresis. And the magnetoresistance is really depending the helicity of the chiral molecules, give you either positive or negative, and even can survive at room temperature. So that's not only in the chiral molecules, also this CISS effect has been also discovered in the hybrid organic, inorganic perovskite materials. And this effect coming from 2018, from the Charles Sargent's group in the Guanghui, they published in Nature Photonics, say, hey, if we have a chiral molecules embedded in the perovskite, which hybrid perovskite materials before was used as very efficient solar cells, right? Compatible with inorganic solar cell in the materials. Now they replaced the organic cations layer, which is in between, the organic layer with the chiral molecules. Then in cases, then you generate spin polarization. That spin polarization will introduce spin polarized photoluminescence, which is circularly polarized photoluminescence. So they study different chiral perovskite, even like the mix R and S 1-to-1 raceme mix, 1-to-1 for the chirality. There's no chiral here, and showing the Zeeman splitting nearly centered at zero field. And if you have a chiral perovskite, then you get a photoluminescence showing this non-negligible circular polarization even at zero field, which is the shift depending the chirality. So indicating the CISS effect also generates some spin current can affect the photoluminescence perovskite. So later on, Valley's group in 2019, they demonstrate, okay, they can also use a similar method that before the chiral molecules, using ITO, chiral perovskite, and nickel ion, by applying autoplane magnetic field and switch the direction field, they got the opposite magnetoresistance, indicating that you can generate spin current through the chiral perovskite and have MR responses within one ferromagnet, like a half spin valve configurations. And most recently, the same group, like with Matt Beard from Unreal, with Dali again, they demonstrate chirality-induced like room temperature spin LEDs. Right, so this have been demonstrated 2 years ago in the APS meeting by Joe Barry. So now the chiral-perovskites can acting as a spin filtering, as spin generator, polarize your holes, the spin polarization for holes, and got to recombine in the CISS-related iodine like emission layer. So then you got the electroluminescence, which is circularly polarized. So that's indicating you do inject spin current from the chiral-perovskite materials, the perovskite materials acting as a spin generator or spin filtering layer, or like even lots of people think that's almost like a ferromagnet, like a magnetic layer, even you don't have any magnetic moment in the chiral-perovskite materials. So the people continue to discuss the CISS effect in different material systems. So now from the Xiangfeng Duan's group, they even can incorporate the chiral molecules in 2D magnet, right? And really in a hybrid perovskite, hybrid materials, but not have to be perovskite, but hybrid materials with intercalated chiral molecule between 2D magnet achieve very high efficient spin filtering effect and magnetoresistance up to 200%. That's coming out of the Nature paper 2022, using a super lattice structure to achieve a CISS effect. They are magnetoresistant. Then from Japan's group, just recently, they also able to generate spin polarization using CISS effect in the chiral superconductors, in organic chiral superconductors. So they based on these simple pictures. Once you have a spin generation through the chiral, you generate a spin up, you must left the spin down into another end of chirality. So it means you should have anti-parallel spin pairs through the CISS effect. So they found a very genius way to detect such a spin pairs into the crystal of the organic superconductors. See how according to different field direction, different orientation of single crystal orientation passing current, you got the opposite anti-parallel spin pair. Further validated the presence of the CISS effect in those materials, further to expand the field even for the chiral superconductors. So when you look at those CISS effects have been demonstrated anywhere, like physics demonstrations, CISS observations, CISS-induced magnetoresistance in all kinds of materials, right? You can work on the DNAs and Otani's group for the chiral molecules. You can have the CISS effect chiral nanocrystal quantum dot. It generates circularly polarized photoluminescence in a perovskite, and also in the circularly in the chiral inorganic crystals. So once the CISS effect has been demonstrated, so different places, as a physicist, we want to know why, right? So actually, in the beginning of the CISS effect was invented, Lolama and his colleagues already introduced a model called like the first model for the CISS effect, that's spin filtering. So what they propose that the helical structure of molecules, any helical superstructure can generate effective magnetic field. That effective magnetic field can be acting on the spin component of the electrons and polarize the spin current. So depending the chiral structure of the radiance and their pitch and also the length, so you have a different chirality-induced electric field and cause magnetic field, effective magnetic field polarize the spin. And based on the calculation, the effective field can be even like 60 Tesla to get very high spin accumulations. But that means you need electron passing through all the helical structures, right? You need electron transmitted through the helical structures. That will work for most of the DNA system and or even for perovskite, but it will not work for the chiral molecules, right? Because chiral molecule, you only have one turns. So electron just through the tunneling effect and how you can have the transmission to get a spin filtering effect generated enough magnetic field to polarize the spin. So then, of course, then people also think about the topological structure in the chiral topological superstructures, give you like Rashba spin optic coupling like band splittings in any of the inorganic chiral structures. In back to 2018, they calculated all kinds of chiral symmetries in the crystals and get some monopoles of rush splitting responsible for the spin generation through the topological state. Then eventually 2021, Binghai Yan's group, they said, okay, so they really wanted to demonstrate the CISS effect in the DNA system without any spin of the couplings, right? So for the spintronic people, we know that in order to convert the spin or to charge to spin, you need spin of the coupling. And also for the topological structures, one important component is spin of the coupling. But however, the CISS effect have been happening in lots of materials that don't have very strong spin of the coupling. They don't have any heavy metals. They don't have any heavy elements. How the spin of the coupling would be concerned to the model to explain the spin Seebeck effect, right? The CISS effect. So that's why the Binghai, they came to our idea, say all the chiral structure contain the orbital angular momentum that have no spin of the coupling. When the optical angular momentum reach at the interface, you borrowed the spin of the coupling from electrode. So then you at the interface, you generate spin filtering and also spin polarizers that contribute to the CISS effect, which just means you have once you have a chiral material itself will not give you any spin accumulation. Instead, once it makes the spin of the coupling in the interface, that may introduce the spin polarizations, right? And also forming some rush bar-like splittings and responsible for the CISS effect. And eventually also people then start to realize, okay, in the chiral crystals, there's magnetic, once you increase the magnetic moment, the CISS effect can be activated by temperature. They start to realize the importance of the vibrationals, also the thermal energy. They believe, like they gave us some insights that, okay, now we see the CISS effect may be thermally activated because those magnetization, the magnetic moment got stronger once they have a high temperature due to the CISS effect. So that implies the CISS effect may be strongly related to the temperature and also vibration modes. So when you see all the major explanations for all kinds of CISS effect, still the origin of CISS effect was not settled down. People questioned and debate, and they have so many theories. It can be explained part of the CISS effect, but not a universal mechanism have been concluded. So we start to study the CISS effect using the hybrid perovskite materials, collaborated with David Wardak and Feng Liu from Utah. So we did lots of spintronic studies in the hybrid perovskite. So once the CISS effect was invented in these materials, how can we miss this opportunity, right? So we contact Wardak and from Pittsburgh, who was the co-founder for the CISS effect, and fabricated the chiral perovskite. And we start to study the CISS effect induced magnetism by photocarrier. So lots of people report the CISS effect in the electrons. You're passing electrons, you got the spin polarizations. So what we're thinking is, okay, how about the photocarrier? Then you have electron hole pairs, and once we shine the light to generate the photocarrier, whether the photocarrier can give you CISS effect, and we can able to measure the CISS effect induced effective magnetizations. And luckily we succeeded, and we shine the light to the hybrid perovskite materials. We generate the photocarrier. So the photocarrier will propagating through the chiral structure, and that's the acting all the spin this through some polarion-based spin exchange coupling that give you magnetic light behavior measured by our Sanyang Moog magneto-optics effect. Then we see the magnetic moment in that interface between nickel ion and the chiral perovskite. We did a lot of control experiment by comparing different chiralities, even for the A, which without the chiralities, with light on and off, we see a very clearly opposite magnetic moment signals related with depending on chiralities. And then we increase the laser power, increase more photocarrier, we see the signal going up, which is where we expanded. as we expected. So the CISS-induced magnetization able to if activated by photocarrier. So after this work, we start to ask ourselves, what's the next step, right? People observe CISS effect in the electrons. People observe CISS effect in the photocarrier by us. So what other quasi-particles can also cause the CISS effect, and what's the what's the physical mechanism behind the CISS effect, explain this phenomenon. So that's why we came to the idea that, okay, so let's generate a CISS effect by the heat current, right? So we can generate CISS effect from electron current, by the photocarrier, photocurrent, and how about the heat current? So that gave us a motivation actually that triggered our research like a couple of years ago, and to achieve this, the chiral-phonons introduced the spin current as part of the CISS effect. And in this work, it's really interdisciplinary work between 4 research groups. Like Li Fa, he's from China. He's the first one invented the chiral-phonon in the PIL paper with Chen Yu, like in 2015. Predict the chiral-phonons in the chiral materials. Where you provide the chiral-perovskite materials with high quality of chiral-perovskite materials. Me for the Spintronics perovskite, and Jun Liu from thermal field for the thermal transport. So it's really interdisciplinary research group make this one work, and to see how the chiral-phonon, the interplays between chiral-phonons and spin current generation can be particularly explain the CISS effect activated by the heat current. So now let's go to the why we related with spin Seebeck and the spin with the phonons, with the interaction between spin and the phonons. That's the field called spin caloritronics, right? So we are able to use the heat current to generate a spin current, and then the spin current can detect by a charge current. So this one effect have been well known back since 2008 by E.G. Saito's group. The observation for the spin Seebeck transfers spin Seebeck into the nature. Then the same group for spin Seebeck in the insulated, and also the thermal longitudinal spin Seebeck in the EX system. And then there are many people working for spin Seebeck for all around the world, right, to make this spin caloritronics. And then also the spin Seebeck can be observed in the dilute magnetic semiconductors, in the antiferromagnet, even in the paramagnet, and also in the non-magnetic materials, right? So you can see lots of similar spin Seebeck responses in all kinds of the same film. But again, so those if you want to see the spin Seebeck, you need in most of cases, you need a phonon to activate the manganon to have a phonon drag manganon effect, and the manganon will emit a spin current, transfer the angular momentum to the agent layer to generate spin, as spin be converted to charges, make such a counterclockwise loop. There's three gradients that the ingredient you need, including spin Seebeck most of cases, the magnetic materials coupled with the manganons. Now, of course, use the magnetic field to switch the orientation of magnetization, also switch the spin informations. So then we start to ask ourselves, how about to use the spin Seebeck in a non-magnetic materials, even have been demonstrated before using magnetic field, right? Back to that Nature paper with the spin Seebeck in non-magnetic materials. So now we don't want any magnetic field, even we don't need any magnetic materials, no magnetic field. So angular momentum carried by the chiral-phonon will make it work. So chiral-phonons is similar to the cyclically polarized light, and which we're using we look at the photons, they contain the EX, EY component, they start to oscillate it with the electromagnetic wave. If EX, EY have different phase delay, they're forming a cyclically polarized light. Similar to the chiral-phonons, you can think about the similar phonon vibration modes in the EX, EY have phase delay. Once you generate such an acoustic wave with optical phonon waves, then you're able to generate such a cyclically polarized phonons, and they can be named as reference to the chiral-phonons. So this chiral-phonon was first predicted by the Li Fa, one of our co-author, and the Chen Yu in the PIL paper back to 2015. They predict the chiral-phonons in 2D materials. in the hexagonal lattice, right? And then you can see the chiral-phonon can contain the angular momentum. So it means we don't need a manganon now, because for spin Seebeck, you need manganon coupled with the phonon, then transfer the angular momentum with the manganons. So now we have phonons itself have angular momentum, can be generated by temperature gradient. So we don't need a manganons, and the chiral-phonon itself can be expected to transfer the angular momentum, give you a spin Seebeck. So the first experimental demonstrative observation chiral-phonon from Xiang Zhang's group back to science in 2018. They first reported observation for chiral-phonons by Han Yuzhu in the 2D materials with tungsten selenide. They observed the chiral-phonons, and chiral-phonon can induce spin polarization state changes in 2D materials. But original 2D materials not typically have a broken chiral symmetry, right? It's a 2D material. It's not the chiral materials. So back to the just recently, the Japan group from Nature Physics, they reported the truly chiral-phonons in the structural chiral system. And here is the mercury sulfide, right? They see this structural chiral system give you chiral-phonons containing angular momentum observed by the Raman spectroscopy. So that means the chiral-phonons can be investigated, can be observed in the 2D materials, and as a dynamic chiral-phonon effect, and also observe the structural chiralities materials. But still, again, there's no connection between the chiral-phonons, the angular momentum, and the spin current. So that's how we introduce our work here. So as I said, the motivations is straightforward. For spin Seebeck, we need the magnetic materials. We apply temperature gradient to generate the manganons. The manganon have angular momentum, can be transferred as an agent layer, and it transfer the angular momentum and polarize the spin current at the copper layer. So that's spin Seebeck effect. So now if we have chiral-phonons, we don't need any manganons. The phonon itself have angular momentum by applying temperature gradient. We driven the non-equilibrium chiral-phonon propagated through the non-magnetic chiral materials. That the angular momentum can in principle can be also transferred, can transfer into the agent layer and give you a spin current. We call the chiral-phonon activated spin Seebeck. So CISS effect, right? So you got a C, you pass, right? So there's a CISS effect. So we start to demonstrate the this CISS effect in the chiral perovskite materials, which we're very familiar with, using a transit magneto-optical effect. We try to avoid using electrical method because when you measure electrical method, you will have lots of other density effect, magneto-thermoelectronic effect. So maybe imposed together, make the model to be more complicated. So in order to avoid those complications, so we're using the Moog measurement, which is a measure like spin current directly using the Moog technique and using the ultra-fast laser to measure time-dependent CISS effect in chiral perovskite materials. So, and these materials, of course, is synthesized by my lovely colleague from UNC Chapel Hill, Dr. Ye Liang and Dr. Wei Yu's group. We embedded the chiral molecule in the hybrid perovskite, forming a layered perovskite materials with all the chiral molecules standard parallel to each other with a well-defined chiral axis outer plane. Right, so that's how we designed our molecule, our perovskite systems. We validated the chirality have been formed in the perovskite materials by measuring CD signals, circular dichroium signals. We see opposite CD responses indicating a different chirality in these materials. So that's our materials and also our motivations. So now we're going to the next section about how we generate temperature gradient, how we were able to measure the spin Seebeck effect driven by the chiral-phonons. And of course, the most important is how you generate the temperature gradient across the chiral perovskite and how to detect the spin accumulations in the ultra-fast time scale, which is similar to the previous talk. I remember 1 month ago, right, for the picosecond spin Seebeck effect, but using the laser as the heating. So that's where we came to my lovely colleague, Jing Liu's lab. His expertise for the thermal generation, thermal transport. he has a tool for the ultra-fast laser, can generate a transit temperature gradient. So we deposit the copper layer on top of chiral perovskite materials, and we shine the light for the copper with 50 nanometers. We absorb all the light, and you generate a transit temperature gradient, which is from hot to cold across the whole sample area. And they can do the calculating with all the temperature gradient across interfaces, including the AC modulated temperature gradient modulated by the ultra-fast laser. And of course, you could be heating it, you still have a DC temperature gradient generated by the continued heating of the laser. Then they were able to formulate a TDTR measurement to calculate what the phonons, what's the frequency of phonons generated in the perovskite, how it's decayed, how the temperature gradient was formed. And luckily, chiral perovskite have very low semiconductivities, and were able to generate enough temperature gradient, and then they enable to generate the temperature gradient to driven the non-colloquium chiral phonons propagating through the perovskite materials. We were able to do simulations. You can see how the DC temperature gradient according to continuous heating, and also the modular temperature heating to laser pulse across the whole thickness of the perovskite sample. Our perovskite sample is like 200 nanometers. Then you can ensure there is a temperature gradient across the whole perovskite as a guarantee of the phonon generations. So that came to the most important experiment, how to detect spin current in the copper layer. So after we're heating the copper, we change the temperature gradient. That temperature gradient will driven chiral phonons propagated through the structure, reach into the interface of the copper, transfer the angular momentum, and generate spin current detected by the probe of the laser. So surprisingly, we see a well oscillated curve signal in the copper layer. Of course, if you choose a non-chiral material, you see non-signal at all, except with slightly similar background. But with this oscillating of the spin curve signal, even larger than more than 4 nanoseconds, is our first feature indicating that some spin current may be generated. And then we switch all the chirality from S to R, with left-handed to right-handed. We see an opposite oscillation of spin current will be generated at the same copper layer and detected by the probe. So that cannot be happened if we're choosing racemic chiral perovskite without any chirality, or the ordinary chiral perovskite, it will only give you some similar background, right? So that indicating the chirality really handedness of the perovskite generates the chiral-phonon, the chiral-phonon generates spin current in the copper layer, and give you like a 2 gigahertz oscillations, which not be able to observe in any other non-chiral perovskite materials. So that's our first observation, and to be a note that there's no magnetic field. There's no magnetic field related. There's no magnetic material have been involved with generate spin current fully caused by the chiral structure. And we also apply different magnetic field to see how the chiral phonons can be related to the tunable by the magnetic field. We see slightly weakly dependence when to apply magnetic field. And then you see how the magnetic field changes the modulation amplitude of your chiral, the C passive effect of spin signal, but not the oscillation in the frequency. So that means it's not generated by the acoustic waves, so which have no magnetic field response at all, right? So also it's indicated slightly different mechanisms to the CISS effect, because the CISS effect, they maintain the spin polarizations at one direction all the time without having any field dependence, right? So since we have field dependence, we kind of exclude this just ordinary CISS effect, and it's not caused by the traditional acoustic wave. It should be a spin signal related with the chiral phonons. And I noticed that one of my colleagues, Jun Liu, presented his work in the last month in APS, this month in the APS meetings, and then also other chiral phonons observation in 2D materials also show a very strongly magnetic field dependence, right? So indicating that it's consistent with our results. So then we try to see, what we can do with the spin current and how to validate the spin current, right? We can see, yes, the spin current has the field dependence. It's not like acoustic wave, but however, how to validate the spin current. So how to validate the spin features of the generated current signal to do the spin current, we're using spin transfer torque, right? So how the spin transfer torque demonstrates the spin current. So once you generate a spin current, once the spin current can be injected ferromagnet, if they have opposite, if they don't have the same polarization, which don't parallel, they generate spin positions. If the ferromagnet, there's a spin transfer torque, that's indicating that you absorb some spin current from the agent layer, can be validated the signal we observe the current signal is a spin current. So the whole process can be well defined by the STT Landau equations, right? You have external field component, a damping term for the ferromagnet, you have field-like torque and damping-like torque once you absorb any spin current from the agent layer. So we first do our control experiment. So we deposit copper directly on silicon dioxide, have no chirality at all. We shoot a laser, generate ultrafast demagnetization. You see only a decay of ferromagnet. And since the magnetic field is zero, there's no oscillation, right? There's no FMR mode. So that's why I just say a decay and back to equilibrium. That's it. There's no STT component at all. So then it turns out that if we replace the silicon dioxide with the chiral-perovskite, so we generate the chiral-phonon, generate spin current, the spin current inject the ferromagnet without any magnetic field. So this one we do at zero field, we see a very obvious the oscillation of the signals of the magnetization. It's not from Moog signal anymore, it's from the magnetization signal detected by Moog, of course, but you see a very well oscillated signal, and which frequency matches our device in the copper-only devices that have the same frequency, indicating the zero field STT signals. And we also initialize the magnetization from the in plane from one opposite direction. It didn't reverse sign. It means it's not mainly caused by the field-like torque, right? If the spin current by the field-like torque, you should be able to see the opposite phase of the STT signal, which is damping term plays an important role for the STT signal we observe here. So then we see the chirality dependence. We reverse the chiral hyperperovskite from the left to right. Then we generate opposite spin orientations, and the STT signal also reverse the phase. So that indicating that the signal we observed before in the copper-only devices, that's really a spin current. And that spin current has all the features spin current is supposed to, and also able to make the spin transfer torque in the agent ferromagnet layer. Well, so that's at the zero field. So how about if we apply magnetic field, right? If you for a simple ferromagnet, you apply magnetic field, you should see a very nice oscillation with 800 nanopicosecond. That's the FMR mode. By plotting different magnetic field, they're able to fit the Cattell equation with the Cattell formula with the regular ferromagnet in the nickel arc, right? So now if we replace silicon dioxide by the chiral-perovskite, for the nickel ion control, of course, you see oscillation with the 1000 picosecond, then later on into the flat. There's nothing happening in the nickel ion in the control sample. However, in the perovskite sample, and you see two modes. One is the FM mode, which is supposed to be one that apply magnetic field, you always have the resonance. We see the FM mode, but after FM mode, you see a very long-lived oscillation signal. This is due to the STT mode by the spin current generation from chiral-phonons. It's in the R, in the S, we both observe different amplitude. However, usually in the R system, the signal is much smaller, but still the oscillation, long-lived oscillation features is presented. And we can apply the different magnetic field to follow the Cattell equations. And most people believe the CISS effect generate effective magnetic field, right? So now if we really generate effective magnetic field, the FMR mode should have a shift, or maybe shift to the high frequency, low frequency, because additional magnetic field. For now, we found that our CISS effect with the chiral-phonons does not generate any effective magnetic field. So it means your nickel ion still all the same nickel ion as before. There's nothing proximity effect, no hybridization effect, change the internal property of FMR. and you see the Cartel equation fits very well as ordinary ferromagnet, but still you see a long-lived oscillation signal at a long time scale, which is due to STT mode due to chiral-phonons. So then we do temperature dependence and also magnetic field dependence. So then you see the field dependence, see how the CISS effect spin current generations changes a function of the magnetic field, seeing like with the asymmetrical responses for the chiral S, with when we change the magnetic field, you see amplitude decrease, amplitude increase opposite field. Also see the phase have been shift, which is consistent with the lots of recent observation of the field dependence of chiral-phonon in 2D materials by Raman spectroscopy, right? So chiral-phonon have the feature to be field dependent, which also consistent with our results here. We do temperature dependence, which will increase the laser power. Then once you increase the laser power, you're able to see temperature gradient is higher. Of course, you see the AC temperature gradient or DC temperature gradient will be increased, and all the signal enhanced at a higher frequency, higher heating power. And then you can also tune the heating power by reduce the modulation frequency in the MOC. Once you reduce the frequency, which means once you keep the average power the same, reduce the modulation frequency of the laser, which is repetition frequency, and the single pulse energy will be higher, then it means the temperature gradient will be higher. Then even the DC temperature gradient is the same because the overall power is the same, but the single AC temperature gradient modulation is stronger, then the temperature gradient is larger, then you are able to achieve a higher CISS signal with this temperature chiral-phonon general spin signals. So then let's spend some time to calculate the efficiency, right? When you talk about spin Seebeck effect, people care about what's the efficiency, how much phonons can be converted to spin current. So first of all, in order to calculate the spin current as efficiency, we need to understand how much spin current we generated. By straightforward thinking, if a chiral structure, you generate a spin current, what the spin position will be? The spin position will be aligned the spin chiral axis, will be z direction, SZ, right? So we see once we measure the polar mode signal, we see the oscillation, which means the z direction of the spin current is oscillating. It's just very easy to simulate it if we have SZ component with the cosine omega t, which omega is 2 gigahertz. We observe a MOC, we should be able to produce the STT signal we observe in a ferromagnet, right? So we do our simulation, assuming we only have SZ component, which is oscillating, and then can calculate the amplitude responses to the STT signal. However, it's different from experiment, right? It's showing a very parabolic increase at the low field, but however, in our cases, we show the magnetic field effect, which increases spin position, which is an STT signal, which doesn't make sense if you only consider SZ component. So that's why we came out that we realized the spin current generation in the chiral-phonons not only around chiral axis, around z direction, actually it's a process, which makes sense. It's a process, the chiral-phonons which are rotating, and the angular momentum in transfer is similar to the AC spin current. So you have 3 components. XY plane with the AC spin current with the rotating, also the SZ component also oscillating. So that's why the overall spin vector should be contained in the XYZ 3 directions, vector direction with the same omega t. So that's why we simulated the STT signal according to our raw data from field dependent STT signal, and we're able to derive the XZ spin position around the SX, SY, which is very small, and also ZZ component. We're able to perfectly reproduce all the spin oscillations in the STT device using such a standard STT signal. So we also generate animations once we have such a spin component, the vector spin current generated by the chiral-phonons with spin density, and they are using the traditional Gilbert damping of ferromagnet with fixed ferromagnet layer with the degrees. You're able to mimic the oscillation of magnetization of the ferromagnet due to the spin transfer torque effect. So not only the small time scale for the for the FMR modes, which is with certain frequencies as FMR, we're also able to perfectly mimic the long-term oscillation, the long-lived STT modes at up to the 3 nanoseconds, with a perfect match our experimental results. So now let's have a quick comparison between the reported CISS effect with the electron-generated spin current and our CISS effect with the chiral-phonon-generated spin current and the traditional spin Seebeck effect. What's their similarities and what's their difference, right? So first of all, if we look at the CISS effect, so there's a table we've summarized all the 2 different components. So the CISS effect, they both don't need any magnetic moment. Yes, they both don't need any magnetic moment. So the CISS effect provides spin filtering generated spin current. Yes, both generate spin current. But for the CISS effect, we observe the very oscillating spin current was never reported in the CISS effect, because all the CISS effect demonstration of the steady state method, they are not in time dependent. No one knows where the CISS effect has oscillating, but the CISS, we definitely see our oscillating of spin current. And for the CISS effect, the traditional CISS filtering effect with anisotropy of spin current only around outer plane. But for here, our CISS effect have spin vector with rotating with the same frequency of the chiral-phonons with the angular momentum as a spin vector with 3 directions. A spin lifetime with the CISS effect have been observed by the previous spin LED paper in the science paper in like 10 picosecond, or maybe longer. For here, because we were driven by the AC temperature modulation, so we can last even more than 4 nanoseconds. And it's very sensitive to temperature gradient. Of course, this is spin Seebeck effect, right? But CISS effect, temperature gradient never reported, but people reported once you increase environment temperature with equilibrium temperature, the CISS effect got enhanced, indicating also related to vibration mode, but not temperature gradient. And typically the one most difference because CISS effect relies on electrons passing through the chiral materials. You need to have electron mobilities, right? However, for the CISS effect, we don't need electrons. Can be very low mobilities, even in the insulated will help. So it means the CISS effect can be even play even more universal materials, including the electrical materials and also for the insulator, as long as you have chirality and have chiral-phonons. So we also compare the CISS effect with the spin Seebeck effect. We summarize all the reports from all kinds of CISS effect reported in the EAG, in the YIG, the cobalt, nickel, and even dilute magnet, in the antiferromagnet. We're able to calculate what's the temperature gradient, which is due to their report, and calculate their spin current due to the inverse spin Hall responses. We can calculate the efficiency of the spin Seebeck from the 20 or 10, even for low temperature for the gallium arsenide magnetic dilute semiconductor can reach like 500 ampere per millikelvin. That was really high at low temperature. So that's how we define our efficiency of the Harman spin current divided by temperature gradient. So since we have a spin vector, which is using a very conservative number, consider T temperature gradient, and using only the small component with the SZ direction, we already got the CISS coefficient around Z direction. It's already 7,000 angstrom ampere per Kelvin meter, which is several orders of magnitude larger than the SSE. But if we consider the spin current with AC spin current around XY component, the amplitude, the coefficient was even much higher. But that's consistent with most spin pumping, right? Spin pumping, AC spin current always have a high magnitude compared to the DC pumping while transfer similar angular momentum. So now let's give a summary what I might talking about it. We're able to generate a spin current in the chiral hybrid perovskite materials, fluid dependent on the chiral structure and the chiral-phonons. We don't need any magnetic field. And the spin polarization, reverse the spin polarization, depending on the handedness of chiral ligands. We're able to demonstrate the chiral-phonon-induced spin current to trigger STT signals which indicating that the spin validated spin current features, and that the spin current generated by the chiral phonon can last very long, even above 4 nanoseconds, modulated by the external magnetic field, modulated by the thermal gradient, and that's the multiple tunable chiral related with the tunable chiral phonons properties as observed in all the other 2D materials. So last, I want to thank all my colleagues, and I thank all my lovely collaborators, my postdoc from WordX initiate our interest in this field. With you for the materials, Jun Liu for the thermal transport, and Li Fa Zhang, who inspired us to use the chiral phonon into spin current, and Feng Liu for the DFT calculations, and all my postdoc, all my collaborating postdoc from different universities, and for PhD students, make this work happen. And of course, I would like to acknowledge, thank my founding report from DOE, NSF, and DOE EFRC Center from the Choice Center. Thanks for your attention.
Thank you very much, Dali, for this very interesting talk. We can use the reactions buttons to thank him for this presentation. So the talk is now open for questions. Please use the raise hand feature in Zoom, and I will call upon you. Tayu, you have a question? Please go ahead.
Yes. Hey, Dali. Nice talk. So I have a question about how critical is the sample quality to see those things that you saw?
Well, it's perovskite. We don't need a very high quality sample, but it's just a spin coated hybrid perovskite samples. Of course, we needed to control very well the morphologies with the make it a flat interface, and also the thickness of hybrid perovskite. But most of the technical challenges, how to incorporate the cation in the perovskite and to achieve very high CD signal. So the chirality is most of the synthesis is difficult.
I see.
For the processing, it should be straightforward. Yeah.
But what about a thickness dependence then?
Well, it's a very good questions. We haven't studied very thoroughly thickness dependence, because in order to have very high quality perovskite materials, the recipe usually for the solar cell recipe, right? So they always give you best morphology at a certain thickness. If we reduce the thickness, the quality is bad, morphology is bad. So usually all the samples we got around 100 nanometers and 150. So that's the optimized for the domain for the chiral hybrid perovskite. But the thickness dependent for the solution process materials is very difficult. Yeah.
I see. Thanks.
Thank you.
Thank you. Dingbing Huang, please go ahead.
Okay, can you hear me?
Yes, yes.
Yeah, thank you, Professor Shen. Very interesting talk. You mentioned that the polarization direction generated by the CISS effect is oscillating and have maybe the component in X and Y direction. Why is that?
Well, great. So that's about our observations, right? So that's how we find out. But the behind the mechanism why it generates such an oscillating spin current still need further investigations. So the one simple picture is if you have chiral phonons, the chiral phonon transfer angular momentum, you may have different angular momentum with all kinds of different directions through the helical structure. So that may contains that. So that can be two parts. It contains the angular momentum, which is in the different orientation with X, Y, Z, or maybe it happened at the interface by chance during transfer the angular momentum. You introduce like an AC component even in the XY component. So we're still doing with our theory group's help, try to elucidating why we have such an oscillation current.
Okay, thank you. Another quick question, like what determines the conversion efficiency, like from chiral phonons to the spin at the perovskite non-magnetic interface?
Well, we don't know the conversion efficiency from chiral-phonon to a spin. The coefficient we launch here is a temperature gradient to the spin current.
Yeah.
Of course, how much temperature gradient generate how much chiral-phonons, I guess there's also another coefficient there. That's not the way our result can detect, right? Probably you need the llama, you need the brilliant light scattering directly measure the chiral-phonons amplitude as a function of temperature. So then we can get the real coefficient. There must be multiple coefficients between the temperature and the spin current, right?
Yes, right. Thank you.
Thank you.
Okay, Matthias, please go ahead.
Yeah, hi, thanks. Very exciting work. I have a question concerning the interface between the perovskite and the copper. I mean, typically you have some oxidation of the copper at the interface. Do you know if that is an issue, and what happens if you reduce the copper thickness and put the permalloy directly on the perovskite?
Yes, so nice question. You are expert here for there is a possibility for the redox and the chemical reaction between copper and hybrid perovskite materials, but as we tried different metals, right? To be honest, we tried really lots of different metals: gold, platinum, and nickel iron, and the copper. It turns out the stability for copper on top of perovskite experimentally, typically on the ultra-fast lattice, is much more stable than other metals. I wouldn't say there's no hybridization effect in the interface, but that's the most stable one. We use it. We also try to reduce. We're also using nickel ion directly depositing on perovskite, and we also observe the similar responses. And there's no problem. Of course, the efficiency and the temperature gradient will be difficult, because if you deposit nickel ion directly on top of perovskite, you may not generate enough temperature gradient. You need a very thick metal layer absorb all the light, right? So when the nickel ion with iron nickel, they may really even have a stronger chemical interaction with the perovskite. So we tried the different metals. We found out the copper, which happened to be the most stable one for this experiment.
Okay, yeah, it's quite a material science challenge. Thanks.
Yeah, great. Thank you.
Thank you. Hongbin Zhang, please go ahead.
Yeah, thank you very much for this inspiring talk. I have a question regarding the material selection. So is there good reason for you to pick up this hybrid perovskite rather than using this inorganic mercury sulfuride? So, you know, thinking of the lifetime of the carriers and so on. Yeah,
so to be honest, the reason we choose the hybrid perovskite because we study lots of spintronic properties of perovskite because we are in this field, and we have a very easy access to these materials because it's our daily job to study perovskite, thin film, doing the solar cells, doing the photovoltaic devices. So materials for us, hybrid perovskite is much easier. And we are another reason we choose a hybrid perovskite because the chiral cations will be easily to be manipulated because you can synthesize all kinds of chiral molecules which give you the best results, right? We tried all the other chiral perovskites too. Most of chiral perovskites also have the similar responses. Of course, the amplitude is different. So for the materials easy, accessible, we choose the hybrid perovskite. But of course, if you have any other chiral materials or chiral crystals, that may also works. But it's not my expertise for this material science field, right? But my expertise in the hybrid perovskite. But since for the 2D material is different because 2D itself don't have any chiralities symmetry. It don't have any structural chiral. It has the dynamic chiral-phonons formation. And if you want to generate temperature gradient through the 2D materials, like monolayer 2D materials, it will be very hard, right? At least you need some thickness to generate temperature gradient. So by considering all these factors, we choose the chiral perovskite to happen to be the best candidate for this study.
Thank you. A short question, a naive one. So there's a so-called there's a concept of so-called spin polaron. So I suspect that this is somehow similar to what you are observing. Are you thinking in this direction, or it is not relevant?
Well, spin polarons, first of all, you need how the polaron formation, you need inject some decent electrons, right? You need decent electrons or holes to be injected hybrid perovskite forming porons. So for here, we don't generate any electrons. We only apply temperature gradient. The mobility and the electron mobility and the conductivity for most hybrid perovskite probably is very low. So we thought that there is a spin poron is a formation in this hybrid perovskite only excited by the heat. But if you excited by the spin current, electron current, like a metal beer, they're doing spin LDD, they pass the current through the hybrid perovskite, of course, you may have spin porons. For here, we only have heat current, a temperature gradient, poron formation may be suppressed.
Okay, good. Thanks a lot.
Thank you.
Good. Faye, please go ahead.
Hi, Dali. Thank you for the nice talk. I think you mentioned that you want to have some non-magnetic material to generate spin current, etc. So this, if I understand your geometry correctly, this is exactly like the spin transport torque, right? So how does your magnetic control efficiency compare to the standard spin transfer torque? And the second question is, how does that compare with the spin orbit torque?
Oh, would you, I cannot hear very clearly about your mic. Or could you repeat the first question one by one? Sorry.
Sorry, can you hear me now? Sorry, I'm in the airport.
Yeah.
Let me actually try my give me one. Can you hear me now?
Yeah, now it's better, much better. Yes.
Yeah, sorry. So my first question is, this is very similar to the traditional spin transfer torque geometry, right? I just wonder how much efficiency compared to the standard, free magnetic layer, fixed magnetic layer geometry. And the second question is, what about the efficiency compared to the spin orbit torque?
Well, first of all, we only compare with spin Seebeck with the efficiency. We haven't compared with the spin transfer torque. So then well, we can do that, but we haven't calculated, which is a very nice direction for us to calculate the efficiency for the spin transfer torque induced by chiral-phonon. But in my hand, I don't have a number because we didn't calculate that, right? And for the second question, the same, because we didn't know yet, but hopefully I can calculate it later once we needed to really calibrate the Moog signal of magnetization, right? And probably with the help of the Xinfan, they can tell us how the magneto-optic detection of a spin transfer torque within the spin-optic coupling, spin-optic generation, like spin Hall effect, and with the chiral-phonons effect. But I think it's an interesting phenomenon and interesting direction to calculate and compare efficiency. But until now, I don't have a number.
Okay, thank you. Alexei, please go ahead.
Hi, thank you for nice talk. So, can you replace ferromagnet by platinum contact and try to see inverse spin Hall effect? Is it kind of compatible? The symmetry of this setup is that type of measurement. Maybe you could see IC signal.
Well, that's we like to try. The first technical difficulty is currently the DC, the oscillation spin current is around Z direction, right? If we apply the platinum on top, the spin current diffusion direction and spin polarization will be parallel. So it will not generate any DC inverse Hall spin responses.
But you also have other components, right?
Yeah,
maybe smaller, but.
Yeah, the other component with AC, yes, we can try, but well, I need to learn how to measure AC ISCG from your field.
But your prediction is quite specific, right?
Yes, yes.
So then, what is the frequency there?
The frequency is 2 gigahertz based on one Moog measurement. The oscillation of AC current is 2 gigahertz.
Okay, I see. All right. Okay, thank you.
Thank you.
Thanks. Ran, please go ahead.
Oh, hi. Can you hear me?
Yes, yes. Yeah,
oh, yeah. Yeah, thanks for the very nice talk. So I just have one question. So in your experiment, it seems that the spin current flow and the phonon flow collinear, so they are in the same direction. So this is the longitudinal geometry. I was wondering if the CISS effect persists if we, look into transverse or perpendicular geometry in which the electron spin current flows in one direction and the phonon flow in the perpendicular direction. I'm not sure if in that geometry there's still such effect.
Well, first of all, we have, sorry, but I think it is a very nice direction. And but first of all, I want to mention is for the chiral perovskite materials, all the chiral axis is autoplane. And
Okay.
actually, most of the chirality, which you observe lots of chiral materials, right, in the chiral molecules, the DNA, the chiral axis is autoplane. So you can only apply temperature gradient along the same z direction, but very difficult to break the symmetry when you apply temperature gradient, which is in the horizontal direction, right? You're not able to generate the chiral-phonons along the chiral axis. I think this question depending what's the direction of chiral axis. Until now, the material in one hand or chiral axis is autoplane. So I cannot do any transverse modes yet.
Okay, thank you.
Thanks. So let me also ask a question. If everything is non-magnetic, phonons don't directly couple to spins, right? You need spin-orbit coupling.
Yeah.
Do you have some thoughts about the actual microscopic mechanism that converts the spin current, the angular momentum from phonons to the spin current, and would it be affected by some interface modification with strong spin coupling, for example, because copper pretty much doesn't have any, right?
Yeah, so that's our difference between our expectation between Binghan Yan's Nature Material paper that he predicts that you need a spin coupling from the electrode, right? Borrow the spin coupling, then you can convert the spin current, the electron current to the spin current due to the Rashba state formation. For here is we predict that we have chiral-phonons, which have chiral-phonon has itself have angular momentum. So once the chiral-phonon will transport into the interface, similar to the spin Seebeck effect. That's why we named that the spin Seebeck. So the spin Seebeck happening when the manganol and the phonon have different temperature once they reach the interface, right? Because there's a slightly small different temperature, you give the spin current injecting the agent layer. So now we may have a picture here is the phonon and the chiral-phonons have different temperature at the interface. So then you can generate a similar like a chiral-phonon drag phonon effect, maybe, but that's just based on my imagination. We do have a theory group behind us. We have some paper on the review and to describe this chiral, how the chiral-phonon can convert to the spin current at the interface.
Well, that was in fact my question. I mean, for magnons, we know there's spin pumping, right? So you can convert in a straightforward way at the surface, but for phonons, it's not quite clear. So
yeah, there is a couple of papers recently. They're about acoustic pumping, right? Acoustic pumping, you can also generate the spin current, can detect by the spin transfer torque. That's you only upon acoustic wave. So that can also generate somehow the spin current if you have a strong symmetry breaking at the interface.
Does it require spin orbit coupling at the interface?
I believe so, yes.
Mm-hmm. So then other materials might have a more efficient conversion because
absolutely. Yeah, absolutely. Yeah.
Mm-hmm. Okay.
We happen to see, we treat hybrid perovskite, we also have a spin orbit coupling too, because we have lead inside, right? Or inherently we have lead. So that's why we already have very strong spin orbit coupling at the interface. So just by luck, we choose a perfect materials that make it work.
Right. So you expect those states would be somehow hybridized with copper, and that would provide the coupling mechanism.
That is a possibility, yes.
Mhm. Okay. Boris, please go ahead. Boris Nadgarny, please unmute yourself.
Yeah, sorry. A very important, informative talk. Thank you. I have a question about chiral-phonons. Is there any critical thickness, or in general, do you see any thickness dependent when you do these experiments? And because you would expect that it's on the one hand, it cannot be entirely 2D, right? It has to be a quasi 2D structure to have these.
We didn't do thickness dependent because that's typically because of materials limitation. So in order to have very well defined high quality hybrid perovskite thin film, we have to adopt the recipe for solution process recipe. That recipe always was optimized for the like 100 or 150 nanometers. If we want to reduce the thickness, like even increase the thickness, the crystallization, the polycrystalline formation, the domain size will be huge, dramatically different. So the answer is we didn't do the thickness dependent.
I see. Okay, thank you.
Thank you. Yeah.
Okay, thank you. I also had a question about this SX and SY, right? So you mentioned that there are transverse components, but what makes them different? I think looking at the numbers, one was almost an order of magnitude larger than the other. So what breaks the symmetry between X and Y? Is that some structural asymmetry or magnetization, or what is it?
Well, you have very good eyes. Oh, hopefully I can. I will escape from that question, but eventually I know someone will ask this for sure. That's based on our observation. We found the longitudinal AC spin current have a magnitude higher than DC, like a Z spin current. So we found the reason that we also do the DFT calculations. You can calculate the phonon modes in hybrid perovskite materials. And you can also calculate what's the chiral-phonon occupation and also the angular momentum by the DFT. So right now, our DFT results implies that the angular momentum actually in the chiral-phonons in the longitudinal mode is much higher than the vertical direction. So that's from the chiral-phonon. So that's, I believe, the spin amplitude from transverse direction, the higher than Z direction, they're coming from the angular momentum of the chiral-phonons. Chiral-phonon around the in-plane direction, the angular momentum is accidentally higher than the Z direction, according to the DFT calculation.
So the Z direction, was it what was the surface normal in that geometry?
The surface normal is parallel with the chiral axis.
So, but is it Z, X, or Y?
It's Z direction.
Z.
Yeah.
Yeah.
The chiral axis and the surface, the normal of the direction of surface, and in the layered structure is always along the Z direction. Yeah.
Yeah. But I think the amplitudes of the X and Y components were also different, right? X was much larger than Y.
Yes, so that's the somehow we don't know because we were not able to directly measure the SX or SY component by our current setup. So the SX and Y, that component is due to the calculation for the STT signal.
Mm-hmm.
That's derived, right? So if you consider like a two oscillation with the cosine omega t, both in the X and Y, they forming the same phase, the fitting for the one component is not that. That's why we choose we have very high error bar for the SY. So basically that may be just the one S with the rotating between different with the cosine omega t, right? But the SY just because another way is not they're not a phase different. So that's what we observed.
Mm-hmm. So you mean you wouldn't put much stock in those amplitudes being that different.
Yeah, I think the X and Y might may not be different just because right now we are doing the STT simulation. We cannot separate them very well. So that's why you can only got one component to be reliable to be fitted. Right?
Okay. All right. Thank you for that answer. And I have a couple questions from Shin. So he sent them to me in chat. I'm going to read them for you. First question is, was the in-plane magnetic field orientation dependence done on the sample with permalloy? Was there a control sample with insulator between permalloy and chiral material to block spin current flow?
We don't have a control experiment which block the spin flow right now. We only use a copper layer. We don't have any insulator layer between the nickel ion and hybrid perovskite. Well, this is a very neat experiment, but we haven't done that way. And we validated the nickel ion internal intrinsic properties with the field dependence. The field also field direction around the 22 degree away from the normal direction, and we got very consistent with the FM mode, which the nickel ion is supposed to be. Yeah. So any such a piece, the nickel ion is supposed to be in plane, right? It's just a 15 nanometers nickel ion as ordinary nickel ion, and the anisotropy is still be in plane. But we apply magnetic field which is slightly tilted, with the 22 degree away from normal angle, but you can also fit very well with the Cattell equation of 22 degrees. It fits the normal FMR mode for nickel ion.
Okay. And the second question was, if there is an AC spin component, can you see from Moog measurement in the first sample with only copper on top?
Yeah, wow, great question. I hope I can. So actually, this question should be go to my colleagues. Why Jane don't design a longitudinal time resolved Moog? Now we only have polar time resolved Moog. We don't have longitudinal time resolved Moog.
But it's possible in principle.
Yeah, it's impossible. So longitudinal Moog for the CW, like a CW longitudinal Moog or polar Moog is easy, but for the time resolved Moog, for the longitudinal mode is not that easy, right? The most of the time resolved Moog is the polar Moog configuration. Longitudinal, yes, we can, but it's require more instrument applications and setup. The student will hate this experiment, but I think there's a reason to do that.
Okay. All right. I think we are out of questions unless someone doesn't have their hand up. Please raise your hand if you have any more questions. This was a nice and lively discussion. Boris, you have another one?
Yeah, I can ask a quick question. So maybe it's a little philosophical question. So is that more or less accurate to think about these chiral phonons as an equivalent of magnons, right? I mean, basically you kind of generate magnons and you have an equivalent of ferromagnetic spin current transfer. How can you think about an antiferromagnetic equivalent of this experiment? In other words, can you look at coupling? Suppose you generate these from two opposite sides from different chiralities. What will happen? I mean, I know it's probably a very speculative question, but
yeah, for the first question, yes, people. We attended the APS March meeting. Some people believe the chiral-phonon is the effective magnetic moment. So similar to the magnons, they also, from the Raman spectroscopy, they see a field, the peak shift as a function of magnetic field, exactly like a magnons, right? But it's in the phonon, in the chiral-phonon, because the 2D material itself is non-magnetic material.
Sure.
So yes, we can equivalently think the chiral-phonon may be similar to the magnons on the current stage, but maybe there's some other differences that I haven't noticed. But now I try to admit that it's very similar like a magnons, just without that magnetic moment. And yes. So what's your second question again?
Well, I mean, basically, from this perspective, can you think about an experiment when you probe antiferromagnetic interaction?
Yeah.
Of these?
So we did two mixed chirality. So because there's a chiral perovskite, we can mix cations with the left-handed and right-handed in the same molecule location. So we did such an experiment. They call this material racemics chiral perovskite. Somehow, once they formula racemics, they're both left-handed and right-handed chirality in the perovskite. It don't have any structural chirality. They just cancel each other, and we don't see such a signal. Probably we need just like a cation antiferromagnet, right? At least for this layer perovskite, all the organic ligands, they are perpendicular aligned. If you have anti-parallel, they will still cancel each other. But for most of antiferromagnets in Seebeck, they have a cation antiferromagnet configuration with a net magnetic moment, right? So that you may see spin Seebeck interferromagnet, but now we haven't seen it within the anti-parallel chirality yet.
Okay, thank you.
Okay, thank you. Again, are there any further questions? Let me check Twitch. Doesn't look like it. So let's thank Dali again for this very interesting talk, and thanks everyone for a nice discussion.